Hello, my name is Rafael Alvarenga, and I'm a graduate researcher in the Compilers Lab at UFMG. In this presentation, I will defend my master thesis entitled Idempotent Backward Slices, a GSA approach to code size reduction. This is a compiler optimization work, and I focus on code size reduction optimizations. I mainly use the notion of a program slice as a compression unit to accomplish this task. I also leveraged different program representations to make the work feasible. My intention is to introduce you to the concept of an idempotent backward slice. But first, let's define what a program slice is. Program slicing was first introduced by Mark Weiser in 1984, and it consists on the following: given given an original program, a selected statement, and a variable, let this pair be called the slice criterion. A program slice is a subprogram that contains all data dependencies or variables used by our selected variable, and also has control dependencies, which are predicates that need to be executed to compute the value of the selected variable from the slice criterion. Uh, Once we outline all statements that influence the computation of the selected variable, we call it the slice with respect to the slice criterion. Program slices has many applications. One of them is debugging. It is the exact abstraction a programmer has in mind when he wants to find a bug at some program point. We can also use program slice as a compression unit to achieve code size reduction once we identify similar functions inside a program. Last but not least, program slices are also can also be employed to parallelize code. That is, given that we have self-contained functions outlined, they can execute independently. To compute program slices, we leveraged two program representations. The first one is the classic static single assignment form. The second one is the gated single assignment form, which is an extension of the first one. For instance, if we want to transform a C program into its SSA form, we need to rename all variables to make their use unique and create 5 functions whenever a variable is used at some merge point in the program. In our case, the 5 function will set y1 to y3 if the last instruction executed was line 2. Otherwise, it will assign y2 to y3 on line 6. The SSA form allows us to accomplish sparse optimizations, but it comes with a flaw. If we want to create a static analysis that needs to know which predicate or condition needs to be executed to make a 5 function assign a specific value to its variable, we can't know for sure because the 5 function doesn't account for the predicate. In other words, the 5 function does not include the predicate x1 greater than 0 inside it. Therefore, this is where the gated single assignment form comes in. It extends the 5 functions to make all predicates explicit to a further analysis. This way, given that we have a program in the SSA form, we can extend it to the GSA form by replacing 5 functions with new functions. The first one is the gamma function, that is a 5 function with a predicate. The second one is the mu function that is inserted at loop headers, and the eta function that is inserted at the exit node of a loop. Finally, we call these functions the gating functions. Let's transform the SSA program in the image into the GSA form. First, we identify P as being x1 greater than 0. Then we identify V1 as being y1 and V2 as being y2. This new gamma function can now replace the old 5 function in the code and produce the desired program representation. Given that I defined what is a program slice and what program representation I work with, next I will define what is an idempotent backward slice and show you an example. Given a program in the GSA form, an idempotent backward slice has three properties: a single entry, the idempotent property, and the slice criterion is a variable, not a pair of statement and variable. For instance, let the C program in the image be our original program. Also, we select variable S on line 10 to be our slice criterion. The next thing we do is to outline only the instructions necessary to compute the value of S, just like the highlighted instructions on the right program. Now, say our program is represented in SSA form in a control flow graph. When we convert the SSA form to the GSA form, we get the CFG on the right. Note that the 5 functions were replaced by either a mu function or an eta function. The GSA program is the one we are going to use to outline a new idempotent backward slice. In this new representation, our slice criterion is variable S3. After we outline all the data dependencies of our slice criterion, we get a new function where its inputs are n, x0, and S0, and this new function only contains the instructions necessary to compute the value of S3. Thus, we have the slice with respect to S3. But now let's say our slice criterion is inside the loop, formed by basic blocks B and C. Then let X2 be our slice criterion. The slice with respect to X2 is going to be limited to the loop its slice criterion is inside. Therefore, X2 slice has only 2 basic blocks. With this example, we can show that an idempotent backward slice has a single entry, because the entry node is the block that dominates all others inside the function. And the slice is also idempotent, because given a bind of values to the inputs, the slice will always reduce the same output. The motivating example of our work was identified on previous work. Wyvern is an LLVM pass that laissify function parameters by outlining all data and control dependencies of a parameter into a new function, so that for that they implemented a program slicer to outline the new functions. But there's a type of graph where Wyvern's algorithm can't handle control dependencies properly. This is the Phrygian graph. Let X3 be our slice criterion, and the program is in SSA form. We start reversing X3 data dependencies backwardly to create a graph of dependencies. So X3 depends on X2, X2 depends on X1 and X0, and so on and so forth. This new graph is called the program dependency graph, and solid edges represent dependencies between variables, and dotted edges represent predicates or conditionals that need to be executed to compute the value of the slice criterion. But there's a problem with this graph. Wyvern's algorithm implements Ferrante's definition of control dependencies. And this notion does not account for predicate B2 that controls the execution of basic blocks B3, B4, and B5. Consequently, the program dependency graph is missing an edge. To solve this, we implemented a program slicer with the following phases. First, we start by normalizing the program using the loop-closed SSA form. Then we transform the SSA program into the GSA program. After that, we try to identify all slices inside a function of the program. Then we outline the identified function and try to merge similar ones to reduce code size. Now, I will focus only the contributions of our work, which is new implementations for the algorithms used on the phases GSA construction, slice identification, and function outlining. We based our GSA construction algorithm on Tu and Padua's algorithm that relies on Tarjan's algorithm for the single source path expression problem. This problem states that given a graph, so a source node S and a target node V, there is a regular expression PSV that represents the path from S to V. We basically want to use regular expressions to represent paths on a control flow graph. For instance, let the Phrygian graph be our input. The entry block B0 will be our source node S. And block B3 will be our target node V. If we take the path of the graph where the P0 condition is true, then the blue edge is labeled P0, otherwise P0 is false. If we keep labeling the graph like this, we will have that the edge from B1 to B3 is the concatenation of B0 and B1, and this represents a path from B0 to B3. Formalizing the terms, P of P0 and 3 is the regular expression that concatenates P0 to P1. And we keep applying the algorithm until we label every edge on the graph, as you can see on the left-hand side graph. The labeled graph is still on the SSA form. The next step is to replace the 5 functions with a new gating function. In this case, the new 5 functions is replaced with a gamma function, and the predicate P inside it is the simplification of both labels at the entry point of block B5. With this new gating function, we finish our GSA construction algorithm. If for now, for example, we want to outline a slice for the x3 variable, just like in the motivating example, we can build a program dependency graph with only data dependencies, and the missing edge P2 to x2 is accounted for. This new graph has only data dependencies because predicates are now accounted as variables used by some other and not a conditional that is inside an if statement. The next algorithm will solve the slice identification phase. Starting from the slice criterion, we traverse the def use chain in a breadth first manner, and the algorithm stops when it reaches a loop header when the criterion is inside it, or at the function entry point. For instance, let's apply this algorithm into the first graph example of this presentation. Let S3 be our slice criterion. Then we begin traversing S3 dependencies. The number inside parentheses is the loop depth of the current variable. S3 is on the main scope of the function, so the depth is 0. If we were talking about variable x2, then the depth would be 1 because it's inside a loop. So we keep traversing S3 dependencies and we find S4. S4 uses P0 and S1, and we keep it iterating like this until we stop. When the stop happens, we have a stop set that is going to be the inputs of to the new slice function. In this case, it is S0, X0, and N. After the program slicer identifies a slice, the next phase is to outline the selected instructions and basic blocks into a new function. The algorithm starts by cloning all selected instructions and basic blocks, then transpose traversed edges and attract blocks with missing edges with new edges. Let the ladder graph be the input of the algorithm. In this snapshot of the graph, the slicer found that basic blocks BB4, BB3, BB6, and BB7 are not part of an identified slice. So it first starts by cloning edges that are part of the slice, and missing edges are created to make branches without targets point to the right blocks that are inside the slice. The first operation we call transposition, and the second one we call attraction. Therefore, the new outline function will have the following graph shape. To evaluate all algorithms implementations, an arbitrary pass named dataless was developed for LLVM 17. The pass implements all phases described before that goes from IR normalization to function merging and simplification. We also modified a build of LLVM 17 to support the baselines. The first modification was to introduce func merging pass that implements function merging by sequence alignment. We also compared our results with the standard IR outliner pass from the compiler trunk. To evaluate all metrics for each experiment, we ran a compilation pipeline that runs -OS before and after the application of a chosen pass. This pipeline was introduced as a patch in the build system of the LLVM Test Suite. To compile 2007 programs from the real world with the 3 passes. For each of the 2007 programs, 4 metrics were collected to compare dataless against the baselines. The first metric is the number of LLVM instructions. The second metric is the size of the text section of the final executable. The third metric is the time the test took to execute. And finally, the time the test took to be compiled using a specific pass. Then for each metric, we counted how many programs from the 2007 ones were affected by the transformation and took the geometric mean of the selected metric for each of them. Negative percentages indicate a reduction, and positive percentages indicate a growth. And the results for func merging and IR outliner were the following. To understand the results level deeper, we asked 7 research questions. The first one was to know the cost model of our program slicer, and we found out that the greatest reduction was achieved when slices had at most 1 function argument, at most 20 instructions, and no more than 10 calls to it. Regarding the code size reduction, we saw a reduction of 9.96% in 23 programs where both the text size and the number of LLVM instructions reduced. The running time of the test saw no significant performance overhead, but the compilation time increased by 4%, almost double when compared to the IR outliner and the func merging pass. Despite the slight compilation overhead, the implementation scales linearly with program size. We also saw that the most time-consuming phase of our slicer is the slice identification phase. Finally, we combined all the 3 passes and saw that executing IR outliner before dataless, and func merging after gives us the greatest code size reduction when compared to each pass running alone. To conclude this presentation, we start by outlining our contributions. That is an out-of-source out of 3 LLVM 17 pass that is open source to the compiler community, a patch to the LLVM Test Suite that makes possible running an arbitrary pass over the entire corpus of programs. But our work has some limitations. The LLVM version is fixed to 17, and the implementation might not work with a different version. Also, our program slicer is a specialized code size reduction tool because we could not identify the compression unit pattern of idempotent backward slice inside the majority of programs from the LLVM Test Suite. For future work, we leave implementing the program slice in some IDE or debugging tools to assess programmers identifying recurrent fragments of code. And also we leave the possibility of implementing a transformation to parallelize programs using the notion of idempotent backward slice, given that they are self-contained in nature. That's it.